Okay. I can see that the mic is moving on my face, so let me know if you cannot hear me anymore. So yeah, the title was Data Realities, blah blah blah. We don't care about that. My name is Otso. I know some of you. I have a background as a software engineer. Actually, my first ever boss is here as well in the audience. And after that, I've been doing a lot of things. This is the second company I've been a founder of. Then I was working at Reactor for a year. And then we founded Valohai in 2016, almost exactly 6 years ago. So we've been doing this for a while now. I'm not a data engineer, so my only claim to any authority on data topics comes from the work I've done at Valohai. Valohai is an MLOps platform, so I think Lauri gave me a lot of really good things in his earlier talk. One of them being that many of the things he was talking about are basically automated nowadays by proper MLOps tools like Valohai, so you don't need to do everything yourself. I'm gonna keep this light and I'm gonna try to keep it simple. So please stop me at any point and ask any questions if you have them. And let's go. Anything so far? Okay. So what kind of data challenges exist in the world? We already got some in the last talk. And this is kind of related. So there could be, like, let's say, satellites going around the Earth, collecting terabytes of data daily. Am I saying daily? Yes. So let's imagine it's like images of the Earth or something like that. And then there is this one guy in Finland. We learned that his name is Lauri today. And his job is to basically collect all of these terabytes of data coming in, run some kind of an ETL process on them, and actually store the data somewhere. So now he has an issue that terabytes is a lot, especially coming from many satellites. Let's say they have 1,000 satellites up in the air. So he orders some more SSDs, maybe 1 million from China to upgrade his data center. You can see he's clearly in Hamina right now. And then there is some stupid evergreen, or what was it called, blocking the SSDs. So he cannot do his job. So this is the reality for somebody, and this is definitely a challenge. But this talk is not gonna be about those challenges. And 99% of the data challenges are not like this. This talk is also gonna be highly opinionated, so feel free to bash on me and prove me wrong. But most of us and most of the data engineers, most of the data scientists, they are not working with data sets of this caliber or issues with the, like, Olkiluoto 3 not starting today or a tsunami hitting Hamina or something like that. No data is the same. The last talk was really great because it was talking a lot about structured data. So we have data which goes neatly into columns in a database. We might have, the source might be Excel files or JSON or weather data or whatever, and we can collect it and we can structure it easily. And then it might be, for example, labeled or raw. So what I'm talking about here is that it can be dirty data. It can be just collected from the streets, and then you need to clean it up so that the data scientist can actually use it. If there is missing data values, you need to handle those somehow and so on. That was a lot about what we were talking about just now. And then I have a high bias. So I'm coming from the world of artificial intelligence and machine learning. And there, well, we are doing everything, but there the biggest challenges are with unstructured data. So we might actually have hundreds of gigabytes or terabytes of data, like those images coming from the satellites or brain scans or whatever. And then I'm seeing specific challenges with the customers that we have at Valohai. You might have seen the scrolling list there just now. I'll get back to that later. And then, in my opinion, most of the data is similar. And this talk is about that. So there are a couple of problems or challenges or opinions that repeat and repeat after time, and they are making Arni, who is our lead developer here, making Arni's days harder than they should be. So basically, if all of you take these points into your hearts, you will make Arni's life a lot better in the future. Just as an example of what would I consider state-of-the-art, difficult, complex, demanding, how many of you don't know what Stable Diffusion is? So there is a lot. Okay, so basically, OpenAI released this machine learning model called DALL-E 2 3 months ago, which you can give a prompt in text. You can say like a group of engineers sitting in a meeting room, Nordic style furniture, everybody has a baguette in their hands. And the machine learning model is going to generate a really realistic image of this. Or we can say that, okay, make it Van Gogh style, and then it's not going to be realistic. It's going to be something completely different. And then like 3 weeks later, after this this model from OpenAI, which is like closed, and they are taking money for using it, then we got the open source version called Stable Diffusion. So any one of you can now go online and use Stable Diffusion to generate images. And it's really, like, you should really look it up because it's really, really amazing what it can do. And this is like an example of the most state-of-the-art machine learning models today. And it's highly demanding. It's doing a highly demanding task, which is like generating images, meaning that the training data it's using is also images. And here is just a quote from this article. And my main point here is that training Stable Diffusion took 256 GPUs running for a total of 150,000 hours, and it cost about 600K. So this is not something you are doing. This is something that the state-of-the-art people are doing in the world. Hopefully many of you get to do something like this, but this is not what most of the people are working on. And then DALL-E 2, maybe that's the most state-of-the-art because it's actually more better, and they estimate that it cost like $4 million USD based on this same computation here. So this is like the high end, and now we are going to get to the day-to-days. So I'd like to keep it simple. I'd like every one of you to think about where we should optimize and where we shouldn't. So it can be money, and then you know that time is money, especially time to market is money. The faster you get out there. Like DALL-E made some money because Stable Diffusion took 3 weeks to get out. If it had come out afterwards, I'm not sure if DALL-E was making any money. So the first point, and here's like an imaginary quote from this could be a Valohai customer, or it could be a data scientist, or I don't know. My data sets are so large that we cannot download them every time we want to run something. And I'm saying that this is false, or sometimes it might be true, but most of the times it's an illusion. And I'm gonna have 2 points on why this is not true. The first one is speed. So we'll get to my first demo, and here we will need to take a short break from the talk itself, because I'm gonna run this on Valohai, and I'm gonna run this in a really, really dirty manner. So Valohai basically does all of these things for you. So if you ever use Valohai like this, please don't. But what I'm gonna do is I'm gonna run in a Ubuntu machine. I'm gonna install the Google Cloud Tools, and then I'm just gonna generate a 10 GB file, and then I'm gonna upload it to Google Storage. So basically my point is just to demonstrate how long does it take to upload 10 GB from a Google machine to Google Storage. Because often we see these cases where somebody is telling me that, hey, we have a 50 GB data set, so it's going to take way too long to download it every single time I want to run something. And like in the Stable Diffusion case, they ran for 150,000 hours. So if it takes, like, let's say half of that is data download, then I get it. It's too long. But let's see how long does it actually take. I'm not gonna make you Valohai experts or give you a demo right now. We can maybe do it as a lightning talk later if somebody wants. But you can think of Valohai for now as a remote execution platform. So I actually started writing the talk like logging into AWS and spinning up an EC2 machine, and then I realized, like, why am I doing this when there's already a tool that does this for me? So what I'm doing here is basically telling Valohai to run something. Then I'm telling it where to run it. I just saw that we have these US Central 1 machines available, so I decided to use those. I'm using Ubuntu 22 version image, and then I'm just gonna paste my code here into the command part, which is gonna run it. And then this is the really dirty part. So I'm actually just passing in my service account credentials file. Please don't do this ever. So let's go. And what is happening now is that Valohai, well, actually I spun it up already before, so I know that there's one of these 1 times T4 machines running. It's running in Iowa, in the US. And then you can see that Valohai pulled the Docker image Ubuntu 22, downloaded the service account JSON, and started running. Now it's installing the cloud tools that I wanted. Let's see where we are now. Yes, unpacking Google Cloud CLI. So it's going to take maybe a minute or two to install. This is a good time for questions if you have any so far. And so after this, we are going to generate the 10 gigabyte file, and then we are going to upload it. And I'm expecting all of these operations to be fast enough that we still have time to finish the talk afterwards. No questions? If not, then while we wait, okay, now it's generating the file. While we wait, I can maybe talk a little bit about Valohai. So actually, the proper way to handle like downloading and uploading stuff would be to let Valohai handle it. You already actually saw that I had one input file here, which was just the JSON file, but I could have generated the 10 gigabytes and uploaded properly as well. And that way Valohai would actually track it. We would get the data lineage that we were talking about. We would get all the traceability, stuff like that. And actually, the next time I would run this, we would have the data cached on the machine. So it would be instantaneous to download it. But I'm skipping all of that because I'm not here to talk about Valohai today. I'm here to talk about data. I think this should take about a minute, so we are hopefully almost there.
Do you know how did Dall-E actually make any money?
They have an API which costs, I think, per request.
Yeah. Okay. So kind of the open source stuff probably destroy that.
Not really, because it's hard to set up still, and the quality is not quite the same.
Yeah. Stable Diffusion also has, I think you can buy like 50 prompts for $10 or something. So they have kind of $100, 100 prompts. Okay. So they have like a similar business model there, but then you can also run it yourself if you just have the hardware or run it online. Okay. Now it's uploading 6.4 gigabytes, so we are almost there. We had the time command there, so we are going to see how long did it actually take once it's finished. So I know that like in a setting like this seems slow, but if you're talking about the 150,000 hours going on after this, it's not really that long. Okay. Which time do we wanna use for these comparisons? The real one? Okay. So 1 minute and 11 seconds. So that's how long it took to upload 10 gigabytes into Google Cloud Storage. So if our dataset would be 10 gigabytes, downloading it should be about the same or even faster. We can actually see Google is complaining to us that we could have actually put this into chunks and uploaded it, so we could have made it even faster, but we didn't want to do that. And then we would need to download it the same way, so that would make it a little bit harder. I think I actually had it here as a second part to download it. I can now see that this is kind of boring, so I will just put it running and then we can continue and see how long that takes or took us. So let's leave that running. And this is again one of those nice things about Valohai. So I'm not running this stuff on my computer. I'm not running it on, well, I'm running it on somebody else's computer, but the platform is handling that. So I can just leave it running and go off. Okay. So hopefully now you can believe me that most of the times the datasets are not too large to be downloaded each and every time you start a machine learning training or something similar to that. If it was a minute for 10 gigabytes, it would be 10 minutes for 100. So it's not really that long in the big scheme of things. It's probably faster than running your tests in a large code base or something like that. Okay, then the second part is price. Does somebody know how much it costs for me to just upload and download this stuff there all the time? Does somebody else know? Any guesses? How much is 10 gigabytes moving from my machine to my Google storage? Less than €1? Yeah, you're right. Because it's free. So it doesn't matter how many times I move that 10 or 100 or a terabyte around, it's free. As long as I'm in the same location, which is what I want to do anyway, because that's the way it's fast. Okay. My second point, this is the classic. We have big data. I really, really love the talk about like the mentions for Spark already before in the last talk, because I was thinking, is this overkill? But I actually wanted to teach you how Hadoop and Spark work from my point of view. Anyone here who doesn't know how Hadoop and Spark work? Okay, great. So then this is useful. So our data cannot fit into a single computer. Now each of these bubbles is a computer, and they can just hold a single number there. So that's the amount of memory we have available, or hard drive, whatever. So what we can do, we can spread it around. So now we have this cluster, and the data is stored all around. So this is kind of like the from the last picture, we had the data warehouse like Snowflake or something like that. So the data is distributed into different physical locations because of hardware limitations. And then we go to this. So this is like Hadoop. So the data is stored in a distributed manner. Then we go to Spark, which is an ETL framework, whatever you want to. I'm not sure what's the official term. And that means that we can run different extract, transform, load operations. And in this case, Spark is a MapReduce platform. So we can run map operations, like for example, +1. So we could say that, hey, into all of these points of data, add 1. Okay, we did that. And we did it concurrently. So this is really fast because each machine is doing this operation independently. And then we run the reduce operation. So we want to sum all of these together. And that's slower than the map because now we need to go to each one of the machines and load the data and do the sum operation. So that's Hadoop, Spark, MapReduce, ETL, all the fancy things that you've heard about and that people rave about a lot. Well, then we get these people telling me that, hey, we have big data, so we definitely need to support Spark. We need this thing now. And there was a question. I also love the question in the last talk about how much data do we need to actually get to the point that we need all of these tools, or rather, would we write something ourselves? Well, and this is now my opinion. So 100 megabytes isn't big data. We can even run pandas.load on 100 megabytes easily and not run out of memory. A gigabyte isn't big data either. We can still do the same thing. We can easily load it up and check our weather data column and see what the weather has been for the last year on average. 100 gigabytes. Okay. Are we getting there? Maybe. It isn't really big data. Like, I was just downloading it in 10 minutes or uploading it 10 minutes, so it's not really that much. It might be a memory issue, but then we can get to, like, for example, Google's high memory machines. I think this was the biggest one right now. I'm not sure if you can pump this up any further, but that's 3.8 terabytes of memory in a single machine. So we can really scale vertically before we need to start doing anything like this. Before we need to hire Lauri to build us our ETL pipeline or read the fancy book over there or wherever it is. We can just push a button and we have this much memory available. So I would argue that if you have 3.8 terabytes, maybe you have big data, maybe you can use these tools. And these tools can be useful like earlier for other reasons than like having big data. But if you have a 100 megabyte Excel file, please don't tell anyone that you have big data and you have the needs that come together with it. Okay. Third point. Let's actually, before we get here, let's see how long the download took. It's probably done now, so just hadn't uploaded the logs yet. Okay, download was slow today, so it took us 2 minutes 45 seconds. Maybe the network was slow or something like that. Faster to upload than download, so probably it's just the randomness we are seeing there. Okay, and then there are actually multiple ways of pushing that number down. So the third and my final point, we can't duplicate our data. So here the imaginary quote is, our datasets are so large that we cannot duplicate them and must move everything in single files. And the point here is kind of to elaborate on this. We had the example where somebody went into the production database and changed the value, and we didn't have the version control available for that. And that's the nature of databases. Kind of, they necessarily haven't been built for tracking every single value change that happens in the database. They are built for storing data. And one easy way, because like whenever we do these heavy operations like machine learning with data, we typically take a snapshot of the data. It could be that we are reading it from the database, but we are still reading it from the database at this point in time. So we are downloading all the weather data from today to a year past from now. We are not including tomorrow's data, for example. So typically the easiest way to handle that is just to take a snapshot of the data, package it up, and then you have it there. And of course, this means that you're duplicating data, because instead of storing pointers to your data set, which might, like I said, it might change. So it doesn't really even work out like that. But instead of storing pointers, we are actually storing duplicates of the data in some cases. And here is now the same point, but now I'm actually arguing kind of the other way around. So one thing is speed. So in this case, we should actually think about speed. And then the other thing that we should think about is overhead. So right now in the first example, we had one 10 gigabyte file, and it was kind of fast to download it and upload it. The overhead to downloading and uploading it was kind of like there was only one event of us calling the Google storage service that, hey, now there's a file coming in and pushing it there. And if we do it for multiple files, that means that we are going to do it multiple times, like all the overhead there. And that also goes to everything from security and so on. But I'll show you what I mean. So let's run the next piece of code. And I'm doing the same thing as before. So again, installing all the stuff. But now instead of creating one 10 gigabyte file, I'm creating 10,000 1 megabyte files, which should, I think, sum up to the same amount. And then I'm going to upload all of them to Google Storage. And now I'm actually even cheating a little bit. So I'm using this -m flag here, which means that we are going to use all the cores available on our machine. So like I mentioned, the big file gave me the warning that, hey, you could have actually split this into chunks and it would have been faster. And now we are kind of doing it. Now we are actually using all the cores on the machine, which will make it run faster. Now we unfortunately need to again wait for the minute or two for the tools to install. So again, any questions at this point? Any thoughts, comments, objections to what I've said so far?
You mentioned the machine that has 3-point-something terabytes in memory. What's the price on that?
You can check.
Because
Maybe tweak some coins.
yeah, if we're talking like price over like if you have 3-point-something terabyte, then you might actually need Spark or Hadoop. 3-point-something terabytes, maybe Spark or Hadoop might be an option there, because if the price is at the point where you're bankrupting the organization basically each time you're trying to train. So
25 euros an hour.
25 euros an hour.
Yeah.
That's not that bad.
Yeah.
Okay, never mind. I take back everything I said.
Yeah, and I actually have a point soon where we can relate to this number. But yeah,
Have you
it's
seen Can My Data Fit in RAM? That's actually pretty fun as well. Just do Can My Data Fit in RAM. Yeah. Yeah, no problem. No problem. No problem.
okay. Thank you. That's a nice website to know about.
Beautiful site as well.
Yes.
Someone really went all out on that one.
So yeah, it probably fits in the RAM. Let's see, what was our code doing? It was popping after generating the files, and then it was echoing. Okay, so now it's copying files. And this is actually like this is not the best demonstration because it's actually kind of fast, even like this. You can see we are now using much of the CPUs here. And you can see we've already uploaded 1.5 gigabytes. It's been running since here. So it started running at I'm not sure how do you say this, 55 minutes. 55:30 was when it started running, so about a minute ago, soon. And it has uploaded 1/3 of the files so far. So it's like 3 times slower than uploading the one single file. I'm not gonna run this through because it would be boring to look at it. So I will just tell Valohai to please kill it. Yes, and hard stop. And then I actually had a last point here, which we can put running there behind the scenes, but it's now doing the same thing again, but before uploading it, it's just tarring it into a single file, not compressing it, but just making it into a single file so that we don't get the overhead of uploading 10,000 like, no, well, they are unique as well because they're random, but like 10,000 independent files. So let's put this running and go forward, and then we can go back and check how quick this is. Okay. I think this was the point where we were at. Okay. Then the second point, price. So what does this cost us? Like, let's say we are like duplicating our data set every time we want to do the weather data thing. I'm using here an example from part of the stable diffusion pipeline. This is not the whole data set that they were using. This is just one part. But just as an example, this one data set that stable diffusion uses, and this was now the state of the art, remember that, is images, and it's like, from where I calculated it, it was like 343 gigabytes. Again, it fits in your RAM. Not the GPU RAM, though. So you cannot like train on that all at once. If we store this in Iowa, where we were, in the standard storage, which is it's kind of like a warm storage, that would cost us $6.86 a month. So it's money, sure. It's like a beer per month. If we have some really old data sets that we want to archive, like we still want to keep them around, but we don't really care about the snapshot from 2 years ago that we trained a single model on, the archive is a lot cheaper. But then again, like let's put this into some kind of a context. So we just had this Kodiklinikka made this salary questionnaire for Finland, and there we found out that the median salary for Finnish software developers, who I would say, well, it's an interesting question, like, do data scientists earn more or less? But let's use this as a number. So if we split that into your days and hours, that means that we are paying you 29 euros an hour. So please don't use that money to optimize this money, because you can see that the scale is different. That's per hour, that's per month, and even then that is larger. And now we get to the, thank you for the question, 25 euros per hour, the high memory machine. That's kind of getting there when it's running, but it's still less than your salary. Okay. Before we go to the summary, let's see if the upload is completed. Not yet. It's uploading. 20. Yeah, it started 21. It's probably going to take the minute again. So yeah, 1/3 done. So let's get back there. So to summarize, my points here. First of all, your challenges probably ain't unique. You are not really doing something. You don't have big data. You are not really doing something super difficult. There are constraints, but they are actually making it easier. So like I mentioned, like for example, GPU memory, all of your data is not going to fit into the GPU memory all at once today. And that means that, for example, in machine learning training cases, you cannot train your model using 10 terabytes of data at the same time, because your GPU can only eat, I don't know, 8 or 16 or whatever gigabytes at once. So it means that you're going to split the data set anyway. You're not going to use all of it at once. And then there's time constraints, like 150K hours of A100 GPUs cost 600K. So you are not going to use unlimited training time on your models either. So those are kind of like these natural constraints for today that you need to take into account, and that makes it easier, because that means that if somebody tells you like we need to move 1,000 terabytes to this training machine now, you can just tell them no, because you're not going to use 1,000 terabytes there today or now. And then my point is that please try to focus on vertical scaling as long as possible, rather than hiring a data engineer team. And well, you can do that. I'm not saying talking about like that, but basically before you start over engineering your pipeline with all kinds of things, or kind of thinking about these problems in a more complex manner than you would have to. And at least to me, that sounds a lot like software development, doesn't it? Okay. Then I have the thank you page, but before that, this is now surely done. 1 minute, 8 seconds. Fair. Yes, fair. Okay, so still at least double the speed of uploading every single file independently. Okay, thank you. And I think Matthias was going to say that let's take questions, but before that, Valohai is probably going to hire the best and brightest of you in the next couple of years. So feel free to contact me, email, call me, check me up on LinkedIn, whatever. Let's stay in touch. And then yes, please, any questions, any thoughts, comments? Was I wrong about something?
What's the salary?
At Valohai?
Yeah.
I'm not sure. I'm afraid that I'm gonna see these numbers often, well, like way more often in the future than I would like to.
It's competitive.
It's not about the salary. It's about working with, for example, Arni here, who is Finland's best Python programmer. Not many people have their own emojis on Koodiklinikka. So there are ways to go forward other ways than salary also. But yeah, competitive.
So you're saying working at Valohai gains you your own emojis on Koodiklinikka?
Possibly.
Possibly one day. Yeah.
Possibly one day.
Find out.
I saw that Valohai instance is using GCP. Is there like a reason you're using GCP, or are you using all the cloud platforms?
Yeah. So Valohai is completely. Let's not go too deep into that. Valohai works with all the major clouds, also some of the more obscure ones like OVH in France, and I think there was one in. Is there one in Israel? Are we supporting those? At least the open stack. Yeah. So the reason why I was not running in GCP was simply because I wanted to use the GSUtil tool for downloading and uploading data to make it fair. Because if I would download and upload it using Valohai, then it would work a little bit differently. For example, here we have support. Like these are. I'm now kind of in a public Valohai, kind of like a SaaS version of Valohai, and you can see we have some, for example, Azure machines set up here in different regions. We have some AWS machines set up in different regions, and this is just kind of like a snapshot out of the environment types that our public SaaS customers have wanted to use, and we have set them up for them. But then most of the customers are actually running inside their own accounts. So that means that they will simply click here, like here is my, let's pick a customer. Here's my ICI, for example, AWS, US West 1, this machine type. They just pick it from the drop down here, go down, press create execution, and now it runs there. So we abstract away all the kind of computation actually happening somewhere on a worker machine. But this was, like I said, what you saw on what you saw about Valoha, don't take that into your heart because I was completely abusing it. Go check out the YouTube video or run the tutorial or something like that to actually see how it works. Or actually, I can run a pipeline for you. So this is kind of the gold standard. Once you have your stuff, once you have your shit together, you will build a pipeline out of all of your machine learning kind of. All of your models are built using a machine learning pipeline, which basically versions how it is built. For example, here there could be like a pipeline where you pre-process some data, you train 3 different models using different hyperparameters. This is amateur numbers. Our customers are running, what was the biggest pipeline, like 160,000 trainings in parallel, something like that. Then we somehow pick the best model and we deploy it online. I'm just going to pick a Kubernetes cluster here quickly, say create pipeline. We are only using Kubernetes. Well, we can also use Kubernetes for trainings, but we are basically using it for deploying online inference models. So now Valoha is running all of these nodes separately, independently, in parallel, as long as it's possible. So for example, this is now running on an Azure F2S machine. We are getting real-time logs, what's happening there, like you saw before. Then the training is probably already started, not yet created. And that's going to train a model and so on until it's going to go into production or test deployment here. Let's see if my deployment is okay. Now there's going to be an interesting crash. Is it disabled? I don't know, it's disabled. That's the reason. I was like, where is my deployment? Yeah. I was like, it's going to fail because I'm going to try to deploy somewhere, which is, yeah. So now we are like training models. We can take a look at some metadata once it starts coming in. So we can, for example, see how the accuracy of our model improves when time goes by. Blah, blah, all these cool things. The graph is a bit funny. So this would be something for a front-end engineer to come and fix. We probably don't need to zoom that far out.
If someone knows how to fix that, please.
So let's see, now there is the find best model going on. All inputs downloaded, still waiting for Docker image. So again, like for example, here you can now see, you can see how we're waiting for the Docker image. It's not a big one, but it's slow. And this is because of the image coming from Docker Hub. So we could also use our own AWS registry or something like that to make it faster, or we could even use like a, what do we call it? The cache, like, yeah, to make it even faster. Okay, now it's completed. So now it's going to start deploying. And while we wait for that, the fastest person here, please shout out a number from 0 to 9. I heard 8. So I think I'm actually doing something. Can I zoom here? Yes. I think I'm actually doing something like the deployment is not that stupid. So we are actually pre-processing the data coming in, but I'm just to make sure I'm just making this data look like what MNIST actually looks like. So this is the data set, the handwritten digits from 0 to 9, which is like a hello world of machine learning. That's the model we trained and deployed. And now there's an endpoint here, link, no file uploaded. So now there's actually an online, there's a HTTP server running somewhere. ready to take requests. And I'm going to test it here through the UI. So I'm just going to send there 19. So I'm going to send there a file, which is the number I just drew, documents 8. And let's see what the model tells us. For the first time, it's going to load the model into memory because that's the way I wrote it. So it's going to take a bit longer. So that's a 3. Yeah.
But it could have been an 8.
Yeah, it's actually 24% sure that it's an 8, but then it's 73% confident that it's a 3.
I think it was the lines that didn't go correctly.
We can try fixing it. Let's make these bigger.
Well, that's an 8.
It's a vertical infinity sign.
I hope it actually.
Didn't you just ask Dolly to like draw us?
Draw an 8 in MNIST style. It's a 0. And it's pretty damn sure it's a 0.
I mean, it's 2 zeros on top of each other.
Yeah. But it's like it could be an 8 as well. It's not like minus to the some numbers.
I would imagine we didn't train enough models.
Yeah, but now like we're talking about all the data lineage and all that boring stuff. So now we immediately in Valohai know where the model was trained. So it was trained in this execution. But we can actually just take a look at the whole pipeline. So we immediately know that the model deployed here was trained here. We can go and see that, okay, the original dataset was this one. So maybe the problem is in the dataset. It doesn't have any 8s in there. Or then our training code is wrong. So we can check the model that we actually deployed for whatever is the problem there. So now we are, for example, tracing this model file that we used in the deployment. You can see here that it's used in the deployment. You can see the whole kind of life cycle of the model. We can see that it was the 5ED. So it came out of this number 45 here. We could go there and take a look at the execution, whatever. We can see that the training accuracy was 97. The test accuracy was 97, 98. So it should actually be pretty accurate. So maybe our dataset is just bad, or then I don't know how to draw an 8. But yeah, that's Valohai in a nutshell.
Was it trained with black or white?
Yeah, that's like the MNIST. That's why I drew it like this. Like the MNIST dataset is 26 times 26 pixels, and it's black, white and black.
But the inference code is actually smart enough to see if it looks inverted, so it inverts it in the inference space.
Yeah.
Because you're not the first one to ask that.
Yeah. Yeah, and actually, like a good example there is also that, like where we had the pipeline here, the part that we called evaluate was actually a batch inference process. So if you would imagine that you have like 10,000 new images and you need to classify all of those, you wouldn't want to push them one by one to a HTTP endpoint somewhere, because that would again be silly. You would rather just load up the model on a GPU machine, load all the images there, and then classify them and return the response. So basically, this is doing the same thing that the online inference code is doing, but it's doing in this execution abstraction. So spinning something up, running it there, spinning it down, saving the results. So here we can see some other images, which we also classified. We can see them here. So here you can see how this is what a 5 looks like normally in MNIST. Here somebody inverted it, made it larger, and somebody inverted the 4 as well. So just to kind of test that our inference pre-processing is smart enough. And like, the way you pre-process your training code, training data, that should be the same way you pre-process your actual data, because otherwise your results are gonna be crap.
If you're a user of Volohi, what like background do you need? If you want specifically like create a model for, let's say, I don't know, some specific cell, like biology cell, not like a cell on a table, but like what do you need to know to be able to do that, like using Volohi?
In Lauri's talk, there was this really nice on the like first page. He mentioned MLOps, and he started with saying that it's like continuous integration, continuous delivery for machine learning rather than code. It's actually also version control, but it's kind of those things together. So then what is left after that is the actual machine learning code. So like, for example, the example that I'm running here, like, okay, let's say I've never used Volohi and I log in here. I could go create an execution if I had the stuff set up in a way, but we could imagine that the stuff that I've set up is nothing. So I could start from echo hello. And now Volohi ensures that, first of all, this is run on an Azure machine. Well, we could also pick a GPU. We can take the Google machine that had a GPU. So now it's running on a GPU machine online. It's running using a Python Docker image. Okay, we actually want to use TensorFlow, so we can run it on a TensorFlow Docker image instead. And then we want to run echo hello. So now, as simple as this, I can just go ahead and press create execution, and it's going to run on this T4 machine using this TensorFlow Docker image, meaning that it has Python installed. It has this very specific version of TensorFlow installed. It has the GPU drivers installed, so it can actually utilize the GPU on the machine. So now what is left for me is to replace this echo hello with my, for example, Python code. So I just need to write my Python code, which trains a model, and put it in place of that. Does that answer the question?
So basically, like, you just need to have domain knowledge.
Basically, yeah. Then there are some parts, echo hello. There are some parts where it's useful if you have some technical background besides that. But with Volohi, it's like kind of the strong point is that Volohi is not an open source tool that you download from Git and set up yourself. It's a fully managed platform. So that means that we have our customer success team working together with all the customers. So everybody has a 2-week free trial where we set up Volohi for them. It's running on their own, for example, Google machines. We set it up. We make sure that they get their own code running up on Volohi. So then it depends on the customer, because like I mentioned, some customers are like highly technical. After the first week, they run a pipeline where they train 100,000 models in parallel. And then in some other places, they are like, I don't really know how Git works, and I've actually mixed tabs and spaces in my Python code, and it doesn't work. And then we are like, here, let me help you. But of course, we draw the line somewhere. But this is not to like I don't have anything against data scientists, but data scientists come from very, very differing backgrounds, and some of them have difficulties running their own Python code. So then we help them with that. But the other customers are like, hey, tomorrow I want to run 1 million jobs in parallel. Can you make sure that it works? And then we are like, yeah, let's take a look at it.
I have more questions, but I'll ask you later to not take away from
Yeah.
from the topic.
I think that's a good amount of questions and demos.
Good product.
Thank you so much for Otso for all of this, all of demonstration and the presentation also. And let's give a huge round of applause for Otso.